Alice, Bob, and Eve explain unitary operators.
It's fascinating how I can rotate this globe any way I want, but it still preserves all the distances between points. Paris and London stay the same distance apart no matter how I turn it.
That's a perfect illustration of a unitary operator in quantum computing.
Unitary operators are absolutely fundamental to quantum computing. They're the only operations allowed in closed quantum systems.
How does my spinning globe relate to quantum computing?
When you rotate your globe, you're changing the coordinates of every point, but preserving all relationships between points. A unitary operator does something similar to quantum states.
Think about it this way. When I rotate this globe, I'm transforming it, but not stretching or squashing it. The shape stays perfectly preserved.
I see. So unitary operators transform quantum states without distorting them?
Exactly. Mathematically, unitary operators preserve what we call the inner product between quantum states, essentially maintaining the angles and distances in the abstract space of quantum states.
Just like your spinning globe doesn't change the physical reality of Earth, countries don't actually move closer together. Unitary operators preserve the probabilities in quantum systems.
So what kinds of operations are unitary?
All the fundamental quantum gates, X gates, Hadamard gates, C0 gates, are unitary. They're the building blocks of quantum circuits, just like and, or, and not gates are for classical computers.
If I rotate the globe 30 degrees one way, I can always undo it by rotating 30 degrees the opposite way. That's another key property of unitary operators. They're always reversible.
Unlike deleting a file on my computer, which isn't easily reversible?
Precisely. Classical computers use many irreversible operations, but quantum computing is fundamentally reversible because of unitarity.
This reversibility has profound implications. It means quantum computations don't lose information, unlike classical computers, which generate heat by discarding information.
It also means that measuring a quantum system, which collapses superpositions, can't be described by a unitary operator. Measurement is fundamentally different from the smooth, reversible evolution of closed quantum systems.
So every time I rotate this globe, I'm performing a kind of unitary transformation, preserving all the internal relationships while changing the overall state?
Exactly. And just as you can compose multiple rotations to get the globe in any orientation you want, we can compose unitary quantum gates to build any quantum algorithm.
That's the art of quantum programming, figuring out which sequence of unitary operations will transform your input state into the output state that represents the solution to your problem.
I never thought my desk ornament was secretly teaching me about the mathematical foundation of quantum computing.